To understand a target population, researchers rarely have the time or resources to measure every single individual within it. Complete enumeration is almost never possible. Instead, we measure a small, accessible subset. We use the statistics gathered from this sample to draw logical inferences about the true parameters of the broader population. But the method of selection dictates whether the math holds up. The first methodological trap is non-probability sampling, which includes convenience, snowball, or purposive techniques. These methods are fast and effective for gathering pilot data or reaching isolated groups. However, they rely entirely on human judgment and logistical convenience to select subjects. Because subjects are not chosen randomly, there is no mathematical way to evaluate the reliability of the sample or measure the random sampling error. We resolve this using probability sampling. In a probability sample, the exact mathematical chance of selection for every single individual is known and predetermined before any data collection begins. Because probability sampling allows us to quantify random error mathematically, it is the strict, non-negotiable prerequisite for statistical inference and generalizability. Simple random sampling, or SRS, is the purest baseline of this architecture. In an SRS design, every single unit in the population has an equal, independent chance of selection. To execute it, you must have a complete, up-to-date sampling frame, a master list detailing every individual unit in your target population. When you have a complete linear frame, like a hospital registry or a student database, systematic random sampling offers a more efficient alternative. This process begins with a random starting node. From there, you automatically select subsequent subjects based on a fixed repeating sampling interval. You calculate that interval, known as K, by dividing your total population size, N, by your desired sample size, lowercase n. While this guarantees an evenly distributed sample across your list, it introduces a specific vulnerability. If the underlying list has a hidden periodic pattern, your fixed interval might accidentally sample the exact same type of unit at every step. Simple and systematic designs are mathematically pristine on paper. In the field, however, they often fail when confronted with the logistical realities of geographically dispersed or demographically complex populations. If you draw a simple random sample from a highly diverse population, chance alone might cause you to underrepresent crucial, smaller subgroups. Stratified random sampling is the architectural solution to this demographic variance. This source image demonstrates how researchers manually divide a population into distinct tiers, or strata, such as socioeconomic status, before drawing smaller, simple random subsamples directly from within each tier. This forces proportional representation. It guarantees that even the smallest subgroups are mathematically locked into the final data. But demographic balance is only one hurdle. Extreme geographic dispersion presents a separate logistical nightmare, where traveling to perfectly randomized, isolated individuals is financially impossible. To solve spatial dispersion, researchers use multi-stage cluster sampling. This diagram outlines the multi-stage branching process. Researchers group the population into geographic clusters, randomly select a few primary clusters, and then sample smaller secondary clusters, like households, strictly within those boundaries. The World Health Organization utilizes a 30x7 cluster sampling method, often employing probability proportional to size, or PPS, to rapidly assess vaccination coverage across widespread areas without needing a centralized sampling frame. PPS is a method where clusters with larger populations have a correspondingly higher chance of being selected for the study. The trade-off is efficiency. Because people living in the same cluster tend to share similar characteristics, cluster sampling requires a larger overall sample size to match the precision of a standard simple random sample. Stratified and cluster architectures dictate how we select subjects to eliminate structural bias, but they do not tell us how many subjects are required to actually prove a hypothesis. Sample size, represented by lowercase n, is never determined by an arbitrary guess. It is a rigid derivation balancing population variance, statistical confidence, and allowable error. To calculate it for a qualitative outcome, such as estimating a disease proportion, we rely on a specific mathematical formula. This equation breaks down the core variables: the estimated prevalence, p, the inverse of that prevalence, 1 minus p, and the maximum allowable error, represented by L. Consider a clinical case study estimating the prevalence of an influenza virus infection in a school. If prior evidence suggests a 20% prevalence, p becomes 20, and 1 minus p becomes 80. If the investigator dictates that the final estimate must be within a 6% margin of the true value, that margin is our allowable error, placing 6 in the denominator. Executing the arithmetic, 4 times 20 times 80 divided by 36 yields exactly 177.78. Sampling mathematics follows a strict rounding rule. You must always round up to the next highest integer to guarantee the study maintains its minimum required power. Our 177.78 becomes 180 students. In this calculation, the allowable error in the denominator is squared. This produces an inverse quadratic relationship. Tighter precision exponentially inflates the logistical cost of the study. As a result, if a researcher wants to cut their allowable error in half, from 6% to 3%, the math dictates they must quadruple their total sample size to maintain precision. Precision scales quadratically, making perfect certainty infinitely expensive. Calculating sample size is ultimately an exercise in allocating finite resources against an acceptable threshold of risk. Even with pristine probability architecture and perfect sample sizing, a sample mean will almost never exactly match the true population mean. This is known as sampling variability. It is the inherent, chance-driven fluctuation of data when computed across multiple different samples drawn from the same population. This diagram plots a dataset of 7,000 children's birth weights. The solid center line represents the absolute true population mean of exactly 3.36 kilograms. Watch what happens when 5 separate researchers pull 5 independent samples of 10 children each. Purely by chance, the means fluctuate widely across the different groups, dropping as low as 3.23 kilograms and rising as high as 3.70. The measurable distance between one specific sample's estimate and the true population parameter is your sampling error. This data fluctuation is not a flaw in the researcher's methodology. It is an inherent property of statistical probability that must be mathematically contained. To contain and predict this chance variability, statisticians rely on a metric called the standard error of the mean, or SEM. This formula shows that the standard error is calculated by taking the standard deviation of the population and dividing it by the square root of the sample size, n. The equation establishes a direct dynamic. Error is tied to the inherent variation of the population, but it is ultimately controlled by the size of the sample. Look at the birth weight data as the sample size doubles from 2 to 4 to 8 to 16. The observed standard error of the means steadily and predictably shrinks. This reveals the mathematical rule of sampling. The observed standard error decreases by exactly 1/2 every time the sample size is quadrupled. As the standard error tightens, the distribution clusters ever closer to the true middle value, minimizing the risk of a wildly inaccurate estimate. Rigorous sampling design does not completely eliminate uncertainty. Instead, it quantifies it, utilizing the laws of probability to turn the chaos of massive populations into precise, actionable mathematical boundaries.